So what I'm going to talk about today is spaces.
We also talk together, but it was
Sorry?
not so fun.
Sorry?
Yes, exactly. She talked to me as well.
No, it's a lot of fun to talk to you, but
And one of the recording
I didn't take it personally like you did. I just assumed that Cornelia was more interested.
So this is joint work with Cornelia and Frederic Haglund, and it's a joint work from 10 years ago, back when we were young and beautiful. We still are beautiful, of course.
You are recording.
Yeah, whatever. So what happened is that we didn't publish this result because we didn't really understand the full, what the implications. And then well, anyway. So here's the result. Is the theorem I'm going to talk about. And it's the following. If X is a space with walls, locally finite, and don't get nervous, I'm going to explain all the terms in a minute, so that the wall metric admits thin triangles. Then the median space associated to the wall space is at finite Hausdorff distance to X. And so as a corollary, we get that co-compact lattices in SON1 or SON1 1 times SONK1 act properly by isometries and with bounded quotient on a median space. All right, so here's a few remarks on those results. So 10 years ago, when we were thinking about that, it was pre-Han Markovitch, pre-Eagle's theorem, pre-Wise's stuff, and it seemed kind of promising that you would get an action with bounded quotient on a median space, because median space is a kind of generalization of cat0q complexes. So it seemed promising that we could maybe extract a finite dimensional cat0q complex out of this action. Now we know that it's not true, and in fact, with Furnos and Yancey, we showed that those lattices cannot be cubulated, cannot act properly co-compactly on a finite dimensional cat0q complex. And Elia Fioravanti, who's a student of Cornelia, I think he's watching us. Ciao, Elia. Anyway, he extended this result to finite rank median spaces, showing that co-compact lattices in those products cannot act properly, co-compactly on a finite rank median space. So in some sense, this is the best we can hope for when it comes to median spaces. And yeah, so 10 years ago, it sounded like a promising approach to make Sagiv's program to prove the virtually Haglund conjecture work. And of course, and now of course, we were far from it. But now, what I take out of it is that I still don't understand why is it that some lattices do admit a co-compact action on a Casio-Q complex and some don't. I mean, I'm part of the proof, so in some sense I do understand the proof, but I feel that I don't understand the real deep reason behind it. And also Cornelia told me that some lattices in SON1 for n big enough are suspected to not be cumulative, and probably also will not admit a co-compact action on the finite rank median space. So here's my plan for the talk. I'm going to talk about median spaces and spaces with walls. Unfortunately, that's not yet in everybody's culture. Maybe in a few years it will be. But anyway, I'll talk about it. And I'll talk about spaces admitting thin triangles. And maybe, and I hope I can give some sketch of the proof, or at least, make a picture to tell you what's the key idea. So
is it correct that it means that the distance in median space and the distance in the wall space are matrix equivalent? Is it the same?
So median space is
We will see.
sort of equivalently can say that they are isometrically embedded into median spaces.
yeah, the embedding is isometric, yeah. Okay, so if I have, to me all my metric spaces are geodesic. So I admit the geodesic between any 2 points, and I will denote by I of xy the interval between x and y. And is the set of t in x such that distance between xt plus distance between ty is equal to distance between x and y.
So that may not be just a single path, right?
That may not be just a single path, and we will say that x is median if for any triple x, y, z, the triple intersection is exactly a point. And the example we can have in mind is R trees also. And the first example where the interval is not a single segment is R2 with the L1 distance. So you take 3 points, like x, y. So with the L1 distance, this is the interval, and z, this is the interval, and the third interval is like this, so you can see that this is m. And more generally, you can see L1n with the N1 metric. And the geometric example is cat-zero cube complexes when you throw away the cat-zero metric on the cubes and you replace it by the L1 metric on the cube. Right, so those are the examples of median spaces. Oh, some example. And they're closely related to wall spaces, which I will now describe. Right, so a measured wall space with a set X with a collection H contained in the subset of X of half spaces satisfying. So what does it have to satisfy? That if H is in H, then H complement right? And you want also a measure you want a measure on H such that for each X and Y in X, WXY, which is the set of H and H such that X is in H and Y is in H complement, is measurable and finite measure. Right, so this is the set of, oh yeah, I didn't tell you, I just said half spaces. And so once you have this data, you define walls. The walls are the set of an ordered pair H complement such that H is in H. So yeah, I'm going to freely put the measure on H or on the walls. But when you write a thing, you have to be more careful. But for the purpose of this talk, just walls and half spaces, I identify the measure. Right, so in fact, I should have said the half spaces, blah, blah, blah.
But you have a map from the set of H.
Exactly.
Set of walls, and that's such a push forward of your measure.
Exactly. There is a natural map from the set of half spaces to the set of walls, and that's indeed just a push forward of the measure. Right. And this is those are the walls separating X and Y. So basically X here, Y here, and you have your H here and H complement here. These are the walls separated. Right, so as an example that you may have already seen are the hyperplanes in a cat-zero cube complex. And this is a discrete example.
Is, in that case, is the complement really of a half space really a half space?
Sorry? Well,
Is
in
the
the cat zero.
complement of a half space because the wall is.
Yeah,
an
right.
actual-
In a cat zero cube complex, you have to be a little careful. What I usually do in a cat zero cube complex is that I just think of the vertices and then
Ignore everything
and
else.
ignore everything else. I think of the vertices with the graph metric, the one skeleton metric. You ignore everything else, and then you get a discrete space, a discrete set of walls. And in some sense, if you take the L1 metric on the cubes, what you add is not very interesting.
No.
It's, you could, yeah, but that's a good point. Discrete. And, right, so another example. Two other examples where R2, and on R2 I take all, well, I could do Rn, all hyperplane. And as half space, I take either open or closed. And bounding open or closed half spaces. And here we have to think a little bit about the measure. And but if you think a little bit about the measure, you will see that I mean the hyperplanes are SO1R modulo SON minus 1R, and you can get a SON invariant measure. And in fact, the measure will correspond. Oh yeah, right. Okay, great. So so this is an example, and another example is HN, again, with all hyperplane as walls. And same, bounding open or closed half spaces. And again, we have to think a little bit why that admits here an SON1 invariant measure. But that can be done. And once you have a space with walls, what you can do is associate a metric space. You get, it's actually a pseudometric space. You define the distance between x and y as the measure of the walls separating x and y. It's a pseudometric space. And when you have a pseudometric space, you can always mod out. And today I'm going to ignore the fact that it's a pseudometric space.
So it's not true that all metric spaces are geodesic.
Well, here is a pseudometric space. So. But yeah, that's not true that all metric spaces are geodesic.
No, but you said that all.
Oh, today, yeah. Okay. Right. So, given a space with walls, I get a metric space. And this metric space embeds isometrically in a median space. Oh, no, I'm going to say something before. because I give you this example. And in the Rn case, with all hyperplanes as walls, the metric space, you get the Euclidean metric. And in Hn case, you get the usual hyperbolic metric. Probably up to a constant. But those it means that the spaces with walls are the natural object associated to Rn or Hn. Great. So right, and so when you have a space with wall, you get a pseudometric space. Let's pretend it's a metric space. And we'll see how we'll embed this metric space in a median space. So, space with walls, you get a metric space. And we'll embed this metric space into a median space. And it's that median space that will be at finite Hausdorff distance to Hn. So how do you get your median space? That's a kind of a standard construction that was known already by Sagiv in the case of codimension 1 subgroup. And in case of codimension 1 subgroup, that gives you cat-0 cube complexes. And if you have the more general notion of spaces with measured walls, you get a median space. So how do you do that? You define M of x bar, which is the set of sections for the projection we gave you here. So it's S is a section for E, and that is admissible. And admissible means that each time you have two walls, so two partitions, a wall is a partition. So two partitions can either intersect or not. They intersect if you have 4 non-empty intersections, and they don't intersect if one of those intersections is empty. So it's admissible if for parallel walls or non-intersecting walls, this never occurs. So it means that once your section picks a wall, it has to pick all the walls containing it. Right? So let's...
So it means that the half spaces always intersect, right? Isn't that just what it means? Because in that case, the half spaces don't intersect.
No, the half in that so if my section was picking that side, it would have to pick that side.
But so isn't this equivalent to just saying the half spaces have to intersect?
No,
No.
because intersecting.
Oh, they're not parallel.
Right. So you say that a wall intersects crosses another one.
If there's
If you have 4 non-empty intersections. Yep. And in this case, for instance, one of the intersections this intersection is empty.
Yeah.
So they don't cross, they're parallel.
No, but I mean the half spaces you've chosen always intersect.
In R2.
Oh, you want, yes.
Isn't that equivalent?
Yes, it's equivalent to the half spaces you choose always have a common intersection.
Okay,
Yes,
just,
yes.
okay.
And, right, so let's look at examples. So, one of those admissible sections is very easy to describe. You pick x0 and x, and your section is x, Sx0 is going to pick whatever half space contains x0. It's going to pick, and then you can see that this is never going to happen. So that's my section. From a wall, picks a half space, is going to pick the side that contains x0. And then M of x is the set of elements in M bar of x, such that the symmetric difference to this special type of section is measurable of finite measure. So and that's going to be my median space. And in the distance between two sections is going to be given by the measure on which of the walls on which they differ. So let's draw a picture. I think it's a nice example. And
So x0 is a fixed base point?
yeah, so you fix x0 as a base point,
Okay.
and then you have, of course, you have to check that it won't depend on the base point. And basically, the reason why it doesn't depend on the base point is because if you have 2 points that are different, whatever separates the walls, the set of walls that separates them is measurable of finite measure. So it's not going to change the space. But yeah, this median space kind of comes with a base point. And right, so let's look at this example. And then see how I used to be good at drawing that 10 years ago when we were young and beautiful. Right.
Which of the two negations no longer hold?
I said, we're still beautiful.
Thank you.
All right, disaster. Anyway, it's not very well done. Anyway, so pick an x0. And so those are my walls. And you can see that so my set is R2. Those are my walls, and you can see that my metric is not going to differentiate in any of those points because they're not separated by a wall. The wall structure is not going to see them. So I can pick x0 here, and the section I'm getting this Sx0. What it's going to do is going to always choose this wall up to here. And when it gets here, it switches direction, right? And when it gets here, again, it always picks that side facing down, and when it gets to x0, it switches direction. And here again, this is what it does. Great. So this is one type of admissible section that we got out of a base point. But as you can see, there are other types. For instance, you keep the same, there are other types. The only condition of the admissible section is on parallel walls. And so if you keep that, you keep that algorithm on this set of parallel walls, keep that algorithm, but then here you're going to do that. You're going to change, you're going to switch somewhere else. And you can see that this no longer belongs to, this no longer is given by a point in your space. It's still an admissible section, but it's no longer a point in your space. So, yeah. Great. So I don't take this one anymore, but I switch here. And so in the median space, I will have all the points that are in X, and that give you those admissible sections, and then I will have some others. And here you can see that this admissible section, the one where I switch here, kind of in another place than X0, this can go arbitrarily far from this one. And this is something that's not going to happen if the metric space has the property of thin triangles.
Do you put a distance on M of X bar?
No, I can put a topology, but not at this. M of X bar, in fact, is the equivalent of the roller boundary for cat-0 cube complexes. For cat-0 cube complexes, there's a notion of boundary, which is the roller boundary. And M of X bar is the median equivalent of roller boundary, and it's something that's being studied right now by Ilya Uravati. It has a ton of tricky technical questions because it's no longer discrete, so there's many things you need to be careful with. All right. All right. So now let me tell you what our space is admitting thin triangles. So at first sight, it can seem to be the same as a median or really close to a median space, but in fact, well, it's not. So XD again is a geodesic metric space. You will say that it admits thin triangles if for any 3 points X, Y, and Z, there exists X prime in the interval between Y, Z, Y prime in the interval between X, Z, and Z prime in the interval between X and Y, such that the diameter of X prime, Y prime, Z prime is bounded by delta. Okay, my delta is chosen once and for all here. So examples you get are hyperbolic spaces in groups. You also have median spaces. And you don't have R2 with the Euclidean metric. And in fact, see, I gave you as an example Rn, and all hyperplanes are as walls. So you could wonder what is the median space associated to it, you get the median space. That's an exercise. You get the median space out of this embedding, I think. Well, you get one median space. XY maps to x sine t plus y cosine t. That's an isometry, that's a median space. And this is an isometric embedding. And you can see that this is an infinite Hausdorff distance from R2. So, oh yeah, and but the metric spaces with thin triangles are kind of fun. I couldn't resist, but giving you some toys. To play with. I hope that everybody has one. I need to. Oh. Well, anyway, so what I drew here is 2 copies of R2. Karen, you don't have a toy?
All right.
Oh yeah, you can give a toy to
Line
Karen.
2, they're the same?
Yes, there's only one. They're the same, different sizes, but it's the same toy. So basically, it's you take R2 with the L1 metric, and so those are the axes for the L1 metric, and you glue another copy of R2 along the diagonal. And so you can see that the square I drew is the interval between x and y, the interval between x and z, and on the bottom space, the bottom sheet, you have the interval between y and z. And the intersection of this interval is along this line. And if you let x and y go really far from this diagonal, you can see that the intersection of this 3 interval is very far from being a point. So typically it has thin triangles because you can anything on that diagonal will do. Any point, any triple point on this diagonal will do. So it has thin triangles, but it will not be. You can't embed it in a median space because you have many points. And in fact, if you take your neighbor's toy and put it like this, what you will see is the building is a piece of the building associated to SP4QP, and this definitely cannot have wall spaces because of property T. So anyway, that's an example of something that can have thin triangles, but is far from, yes?
So is it equivalent that any asymptotic cone is a median?
No, I don't think so. I think you can have thin triangles and asymptotic cones that are not median. Typically this one. If you take this guy, so it's this 2 copy of R2 with the L1 norm, and you glue it along the diagonal. If you take the asymptotic cone, you're going to not move from that, and that's not median. You seem to disagree.
I don't know. I need to think. I'm thinking. I'm not disagreeing. I'm thinking.
Okay. And so, yeah, so I think that what's equivalent is if you furthermore assume that the locus of such triple is uniformly bounded, then you're going to have a median space in the asymptotic cone. But what this toy shows is that the locus of this triple of points doesn't need to be uniformly bounded. It can grow.
Linearly with the distances. So the asymptotic one doesn't change.
And apart from that, I don't really know much about spaces with thin triangles. Some time ago, Murray Elder showed that they had a subcubic Dane function, and I don't know. I've heard the rumor Bill Thurston back then could show that it had quadratic Dane function, but that never materialized. Maybe I misunderstood your numbers. But anyway, so I think they're nice objects, but I don't really. I mean, I have a few examples, but I don't know. Well, one thing that's easy to show is that definitely the Hn plus Hn with the sum of some metric. And another thing that's pretty straightforward to show is that if you're hyperbolic relative to a subgroup that has thin triangles, then you have thin triangles. But yeah, otherwise, I don't really know what those are, apart from those examples. And yeah, in the last minutes, I promised to wave my hands and tell you something about the proof. Maybe I'll just draw some pictures. Some time ago, actually a long time ago, when I was a postdoc at Cornell, Karen had told me that it was very important to draw pictures when we give talks. And I came from a place where people didn't draw pictures. So I try to draw pictures. I think it's fun, right? I hope you appreciate the taking it to the next level and bringing it towards to people. So, right. Oh yeah. All right, idea of the proof. So what I wanted to show that if X is a space with walls, mu locally finite. So I'm going to tell you now what mu locally finite is. Such that the associated metric space admits thin triangles, then M of X, then in this embedding, the image is finite Hausdorff distance from X. So basically you have your X, which is your space with walls, and you're going to add some stuff. So X gives you all the sections that come from those points. You're going to add other sections. You're going to add some stuff. And what I'm saying is that when the metric has thin triangle here, then whatever you add is at finite Hausdorff distance. So, oh yeah, I didn't tell you what mu locally finite was. I think it's not very important. It means that the measure of the walls intersecting a ball of radius r is finite. actually, is bounded by some. We
Uniformly.
yeah, it's uniformly locally finite, exactly. So independent. Right, so the technical lemma the technical key lemma is the following, is you have x as in the theorem, and if you have a convex set, and each time you take x here, you look at an epsilon projection. So P is an epsilon projection on C. It means that, means what? That the distance between x and P is bounded by the distance between x and C plus some epsilon. Yes. So it's almost a projection. And right, then you're going to look at the walls that separate x and P but intersect C. The walls that separate x and P and intersect C. So it's the wall that separates x and P, and you subtract the wall that separates x from C. So you want this measure to be less than or equal to 2 delta plus epsilon. And so the reason,
Where is delta?
oh, the delta
Okay,
comes from the
triangles.
thinness of the triangles. Yes.
Where it always comes from, never
Yeah.
mind. That was obvious. I was falling asleep.
Yes, sir, I interrupted your morning nap.
Yeah, I know.
You didn't seem to be sleeping.
You're sleeping.
So, right. So how do you do that? Basically, you pick a Q here, and then, since we know that there is a thin triangle, and this is convex, there will be a thin triangle that does like this. So this, since by convexity, will stay here, and here by convexity of the wall, well, yeah, I forgot to explain that. Anyway, walls are convex. So you will find a point P prime here, a point Q prime here, a point X prime here, and a point Q prime here. And because, so by thinness, all those are closed. And since P is epsilon projection, it means that P, this going like this is not very far from going along the geodesic, along that geodesic. And it also means that P, so P is an epsilon projection, means that P is close to Q prime, hence to X prime and P prime. So it means that H, in fact, belongs to a wall that cuts a small ball around P. And by mu finiteness, we conclude this technical lemma. anyway, so that's the main technical lemma. It means that when you look at the wall separating 2 points, an epsilon projection, and the wall separating this from a convex set, you won't miss much. And then that's going to that's the main geometrical point in the proof, and then the proof is pretty straightforward from here. And I think that since we have another talk at 11, I'm going to stop here. And thank you for your attention.
So for the ignorant, so in dimension 3, hyperbolic lattices, they are cubable,
Yeah.
but in higher dimensions they are not.
So I don't know. I think that some of them are. Isn't that? Yeah, I don't want to say too much stupid thing online already.